Good day, graduate learners. Welcome to today's physical science lesson. My name is Mashidu Mamburu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. As I've already welcomed you, today we'll be dealing with a revision of paper 1, that your topic is mechanics with wave, sound and light, electricity and electrostatics. And then as we start, you will remember that paper 1, it has these knowledge areas, which is your mechanics, your wave, sound and light, your electricity and magnetism, your matter and materials. And if you can look at the marks there, we have 65 marks that comes from mechanics, wave, sound and light 15, electricity and magnetism 55, matter and materials 15. You will have seen that already under for this June. You matter and materials, photoelectric effect, you haven't done it yet. So our focus will be mostly on those topics, which is mechanics, wave, sound and light, electricity and electrostatics. So that will be our focus. I will ensure that you are able to pass. The paper is out of 150 marks, is 3 hours, and those are the cognitive levels. Now, if you check our question paper, is always structured in this way to say we always start with section A. Our section A has 10 multiple choice questions with 20 marks. Please spend some time on multiple choice. At least allocate about 2 minutes there for each question so that you are able to get all those 20 marks that is awarded on section A. We are left with 130 marks, which is now section B, structured or long questions. And then the total is 150. As I indicated, we have a 3 hour paper. Now, under mechanics, we'll start with Newton's laws of motion and forces. You will remember that you have done N1, Newton's first law. You have done N2, which is your Newton's second law. You have done Newton's third law and Newton's law for universal gravitation. Under Newton's first law, you will have known that we are saying that an object will remain at rest. So that is the first thing that you must see, that the object must remain at rest or moving at constant velocity. So that's how you start your Newton's second law. You'll say an object will remain at rest or moving at constant velocity unless acted upon by an external resultant force. So that is how you must state your Newton's first law. And then we are saying Newton's first law, F net equals to 0 because the object is at rest. When the object is at rest, it means that there is no more motion, which means that our acceleration is 0. When it's moving at constant velocity, it means that the final velocity and the initial velocity are equal. And then if you look at the change, which is final velocity minus initial velocity, it will give you 0 as well. So we're saying F net equals to 0. Another thing that I must add on Newton's first law is that the forces are balanced. If the object is having balanced forces, as well, we'll talk about Newton's first law because F net will be 0 newtons. Now, when it goes to Newton's second law, we are saying F net is no longer equals to 0. We are saying that F net equals to MA. So you have to remember that as and when we say state Newton's second law, you will say when a net force, so you're just adding when there on the net force on the left, to say when a net force is applied on the object has mass m, the object will accelerate. So you are able to look at F net equals to ma. It reminds you how you must define or state Newton's second law. We are saying when a net force is applied on the object will accelerate in the direction of the net force. Don't forget the last conclusion where you are saying acceleration is directly proportional to the net force and inversely proportional to the mass. So that's how you would state Newton's second law. When we move to Newton's third law, now you are saying we still have two bodies here. So we are saying when body A exerts a force on body B will exert an equal but opposite force on body A. That is a simultaneous force that is being applied. Hence, we are indicating it with a negative there to see that, okay, we have force A that is applying on the object B, and we have force B, object B applying a force which is a negative one, because we are showing that they are indifferent, they are in opposite direction. So you have to remember all these Newton's laws of motion for your preparation of your question paper as you'll be writing. Problem solving strategy. Remember, this is our focus now to say how are you going to solve these problems as you come across them tomorrow. I've already indicated that the definitions, you must know them the same way they are indicated in the exam guidelines. So we're saying in application of the Newton's law, identify the forces acting on the object. So the first thing will always be free body diagram or force diagram. Sometimes we'll ask you to draw the free body. Almost all the time we're asking you to draw free body or force diagram. But we are saying be able to draw free body diagram or force diagram and to be able to see the difference between the two. And we are saying always underline keywords. As you are reading statement, when we say rough surface, you know we are saying there is friction. But when we say smooth surface, we are saying there is no friction. Sometimes we are saying frictionless surface, which means this is a smooth surface, we have no friction. So be able to know the language so that it becomes easier for you to answer the questions. We're saying pay careful attention to the mark allocation. For example, if you have a question with 3 marks, for example, you know it will be a routine question where you just have to indicate the formula, the substitution, and the answer. Remember, if your answer, you have always to write there, SI unit there, and then we're saying if it's a vector, you must write the direction. Hence, I'm saying FSAUD, which means you write the formula, you substitute, you write the answer with the correct unit. Remember, if you write the correct answer without a unit, it will penalize you a mark. So always when you're writing a final answer, ensure that you are writing a correct unit and you are indicating a direction. Remember, direction will only indicate it if you are dealing with vectors. But if you have questions that have more than 4 marks, that will be multi-step, where you have to now follow different steps to answer the question. So always the marks will tell you the type of question that you are dealing with. Now, we are always starting with 2 things that I'm emphasizing. It's the exam guideline. That's where you're getting all your definitions and all the content that you are supposed to cover. Number 2 is the data sheet. We're saying this must be your friend. Exam guideline and data sheet. We are saying now with the data sheet, you are able now as well to see that the data sheet of forces, which is for those question 2, and for your momentum question as well, you will be using this data sheet. So be able to know that if we're saying state Newton's second law, you are able to know F net equals to MA is indicated in the data sheet. If you are saying calculate static frictional force, you are able to use that formula. Kinetic frictional force, you are able to utilize that formula as well. If we say calculate the weight, you have the formula given there, as well as if we are saying now calculate the the force for universal gravitation, you are able to utilize that formula. So it's important that you are using your data sheet, because if you are able to identify the correct formula, you are able to substitute, you will be able to score some marks. So as you prepare, as you revise for your paper, ensure that you are ready in terms of that one. Now, I've already talked to this slide to say these are the mark allocations. So mechanics, you got to spend some time there. Electricity and electrostatics, you got to spend more time there. You have your Doppler effect there with 15 marks that you are having. That is the structure that is you are supposed to follow. I've talked to that one as well in terms of the mark allocation. Now, in terms of the Newton's laws of motion, if I can just move with you quickly, let's look at an activity there. The activity there is saying a block of mass 1 kg is connected. So it's very much important that as you are reading, you are having a highlighter. A block of mass 1 kg is connected to another block of mass 4 kg. You can see the diagram is showing you them there. The angle there is 30 degrees, as indicated, a certain angle of that with the horizontal. And we're saying the force that is being applied there is 40 newtons, parallel to the plane as shown in the diagram. The magnitude of the kinetic frictional force between the surface and the 4 kg block, so is this the frictional force here? We are saying there is 10 Newton force. But when it comes to the 1 kg block, on this block, we are saying you are given the coefficient of kinetic friction, which is 0.9. Immediately when you see the coefficient of kinetic friction, you must be able to remind yourself to say, we said we have this formula, which is the coefficient of kinetic friction times the normal force. That must be able to help you to calculate the kinetic frictional force across the 1 kg. So obviously, when you see the coefficient of kinetic friction, you know exactly that we will ask you a question to calculate, or we will need you to calculate the kinetic frictional force that you will be able to use in the formula. So the data is important because it's informing you that for this one, we said it's 10 Newton for the 4 kg block. But when it comes to the 1 kg block, we only gave you the coefficient of kinetic friction. Then you are able that you will utilize that to calculate the frictional force. Now, the first question there is saying, state Newton's third law. As I've indicated, we just stated them now. You will see that our questions, most of them, the first question will be state, will be define, and all that. So it's important that you know all the definitions. Remember, for all your questions, if there will be 1 or 2 definitions, you must be able to collect all those marks. So we're saying, state Newton's third law of motion in weights, and then draw a level free body diagram showing all forces acting on the 1 kg. So we are being specific here to say the free body diagram you are drawing, it must be of forces acting on the 1 kg block. And if you see there already, we said we have a 40 Newton applied force there. You can see we have a string there. We have so there must be tension there. And because we are given coefficient of kinetic friction, you know that there must be frictional force. Already you can see that there are 3 forces that are acting there, where we have the applied force of 40 newtons, we have the frictional force, and then we have the tension that is opposing the motion there. And you know that we have the normal force that is acts always perpendicular to the surface. So you're going to have the normal force that is acting perpendicular to the surface, and then you have the Fg that is always towards the center of the earth, that will be going downwards. So as you are thinking about drawing a free body diagram, those are the things that you will be considering. Now the other question in 1.3 is saying calculate the magnitude of the kinetic frictional force between the 1 kg block and the surface. Already I've indicated you are given the coefficient of kinetic friction as 0.29, and that is going to help you to ensure that you use that 0.29 in order to calculate the frictional force there. But what is important here, because we are having an incline, you can see we have an incline there, is different if we are moving, we are having a horizontal body. If our body was horizontal, remember, if our body was moving like that, you will have seen that we are going to have our normal force acting in that direction, and that normal force will refer to it will be equal to mg. I'm bringing that so that, because we don't know how the examiner will ask you the question, to say if now the object is on a horizontal, normal force will be equal to mg. But if it's in an incline, now it changes to mg cos theta. So it's very much important that you see the difference of the normal force when we are dealing with a horizontal surface and when we are moving on an incline. So you will see and when we do the question, 1.3.2 is saying calculate the tension in the string. So we're taking the T here, the tension on that string. We're saying calculate it. And you can see that this tension is between the 1 kg block and the 4 kg block. So you will know by now that you have to apply Newton's second law in each of these two blocks. So you'll say F net equals to MA for this one, where you will write all the forces acting on it. F net equals to MA on the 4 kg block. Then you are able to solve the problem. If I may move to the solution, say this is how now you would move to a solution to say state Newton's third law. You are saying when an object A exerts a force on object B, the object B simultaneously exerts an oppositely directed force of equal magnitude on an object A. So we talked about that, hoping that you have understood. Now the next question, we're saying draw free body diagram. As I was showing you how to go about drawing the free body diagram, you will draw, it's better, you just make a dot there, then you draw all your forces from that particular dot, and then you are able to see the mark, which is 5 marks. As we allocate the marks, we are saying there is 1 mark for the normal force, 1 mark for each force will be allocated 1 mark. So the number of marks are able to show you how many forces that we are expecting on a particular question. I hope that will help you as you deal with many questions that comes. Remember the question on you calculating now the kinetic friction force on the 1 kg. Remember we're saying on the 1 kg we're given the coefficient of kinetic friction as 0.29. So you are simply multiplying 0.29 with the normal force. But our normal, because it's not normal, it's not on the horizontal surface. Our normal now has cos theta, so it's mg cos theta. As you can see there, for our normal it's not mg, it's mg cos theta because it's on an incline. So always differentiate how to calculate, how to get the normal when we are in a horizontal surface, which is mg, and when we are in an incline, which is mg cos theta. I think I've overemphasized that. You won't forget that and lose marks. And we are saying that now you will write your coefficient of kinetic friction, which is 0.29. You multiply it by mg cos theta. Our mass was 1, our g is 9.8, our angle was 30 degrees. So you are able to get your 2.46 Newton as the kinetic frictional force that we are getting. And then you can as well use this method of using proportionality to say 1/4 of the larger mass, and then you know 1/4 of the 10 which is the 10 Newton of the 4 kg. Remember the 4 kg block, it had 10 Newton frictional force. Then how much will a 1 kg, the ratio, the issue of ratio is 1:4. 1 kg is to 4 kg. So if you say 1/4 multiplied by 10, you are able as well to get the correct answer, which is 2.59 newtons, and we'll be able to award you all your marks. So we're hoping that will help you as and when you are dealing with questions related to this one. Now, remember the last question that we talked about. We said now we're going to calculate the tension on both the 1 kg block and the 4 kg block as they were moving in that order. So we are saying now you will apply Newton's second law on this one, the first block, which is now the 1 kg, and you apply it on the 4 kg. So it's important that even if we didn't ask you to write down the free body or force diagram, but you have to identify the forces in all of them so that you are able to utilize them. Now we'll start with the 4 kg one. You'll say for 1 kg block, you are now able to write the F net. You identify all the forces that are acting on that one. Already we have agreed is the 40 Newton of applied force. We have agreed we have tension and kinetic friction, which all of them are opposing motion. Hence we are writing them as negative there. And then you have FG parallel, which is your mg sine theta. Remember, you will only resolve the forces now when you start doing the calculation, not during the drawing of the free body diagram. Then you are able to do all your substitutions. Our mass was 1 times A, you are able to get that. And then you get your formula there, which is 32.64 minus T equals to A. And you are calling that equation number 1. And then you go to the 4 kg block, you apply again the F net equals to MA. You will only be awarded 1 mark for F net equals to MA because you are going to utilize it for all of them. And then you identify the forces. You have the T there, the tension that was going in that direction. And then you have the mass, which was 4. You have the that is mg sine theta, which is now opposing as well because it's going downwards, and friction as well is going downwards. Then you are able to subtract those, and it's 4A, 4 for the mass and the A. Then you are able now to say from 1 and 2, you are able now to equate the 2, and then you are able to get your tension at 32.04. So always practice how to use these simultaneous equations. You will apply Newton's second law on each block separately, and then you are able now to use your math skills there, and you are able to determine our tension. So that was our first question, which was based on Newton's laws. Now, if you look at second topic now, which is vertical projectile motion. Now, what are we saying here? We're saying under a vertical projectile motion, the first thing is remember the definitions, and we have 2 important definitions for this question. Is the definition of what is a projectile and what is free fall. I mean, you can't go and write exam without knowing those 2 definitions. So you must know what is a projectile. So a projectile, we're saying, is an object which has been given an initial velocity. So you have an object that has been given an initial velocity, and then it moves under the influence of gravitational force only. So it moves under the gravitational force only, and it has been given initial velocity. So you know that is a projectile. When it comes to a free fall, we're saying free fall is a motion. So the difference is that projectile is an object, free fall is motion, during which the only force acting on the object is the gravitational force. So you will be correct to say a projectile undergoes free fall. So when you have a projectile, well, immediately when I throw something, it leaves my hand, it's now under free fall, because as long as the only force that is acting upon that object is the force of gravity, that is free fall. As long as the object is in motion and the only force acting on that object is the force of gravity, then that is a free fall. So a projectile undergoes free fall. So please know those definitions and always remember them so that you are able to get your correct answers. Now, the other thing that you must focus on when you're dealing with this question of vertical projectile motion is the issue of graphs. You must be able to draw the graphs, the position versus time graph. You will have seen that mostly our position versus time graph, we're finding them as curves like that. And then we're having velocity time graph, which you will have seen that we're talking about straight lines, can be moving like that, can be depending on what is given. But when you're finding graphs that moves like that, you know that those are your velocity versus time graph. And you have your acceleration versus time graph, which most of the time you will see. Remember, your acceleration can be on the positive, it can change direction as the object changes the direction, then you are able to have it on the other direction. So be able to identify what type of a graph. If we're saying sketch velocity time graph, you know that you are dealing with straight lines. Those straight lines as they move, as I've indicated. If we are saying acceleration versus time graph, you just check whether it's starting from negative to positive or from positive to negative. The same with your position versus time graph. So remember to do that. Sometimes we'll give you a graph. You will see as you do questions, we give you a graph, then we ask you to determine the position, the velocity, and the time. Sometimes you'll be given a graph and be able to describe the motion as and when you use it. Remember, we have 4 equations of motions that we are going to use, and then these are our 4 equations of motions. I hope by now you have them. They are on the data sheet, so you don't have to worry. The main thing is that you will be informed by the data collection. Please, always before you answer the question, have data collection so that you collect data that will tell you which formula will be able to help you to answer the question that you will be asked. Now, as we move to problem solving strategy when you are dealing with vertical projectile motion. So what are we saying here? We're saying the first thing, draw the trajectory followed by the projectile. We are saying this projectile, how is it moving? First draw, have it as a picture so that you can be able to understand what is happening. You can see here on the right, we've indicated and we have even labeled there A, B, C, D. You can see that we had an object at A that was being thrown upward. So if we are saying an object is thrown upward, you are able to draw it, and you know that as an object goes up, it will reach the maximum height. So you're able to have AB as part of your trajectory, and then the object can go and reach maximum height. It can come back to the thrower's hand, that is C. Sometimes it will come back, then the thrower can catch it. So sometimes it can pass, then you are able to pass. So even when you say draw position versus time graph, you just draw something of this nature, you are able to see what is happening in terms of the trajectory. So this trajectory, it helps you understand the problem. We're saying don't eat the whole of this big question at once. Eat it piece by piece. If you are able to solve between A and B in order for you to determine anything that's needed there, it makes it much easier than when you have to deal with the whole diagram without having to label your trajectory, your part of the object. Now we're saying put critical points in your trajectory, which is what we have done. Initial velocity when the object was thrown, maximum height when it comes back to the thrower's hand, or when it passes, when it reaches the ground. So you're able to put points there. As I've indicated, it's a point of launch, maximum height, point symmetrical to the point, that is the point symmetrical, same as A. Choose sign convention. It's you choosing sign convention to say upward is positive or downward is positive. So you must be able to always choose the direction as well there. It's important that initial velocity and velocity at the maximum height, you are able to look at that. That is the first thing that you look at. You will write there. Hence, we are showing you that under this vertical projectile motion, we have 5 variables. And in your table there, as you do your data collection, use that table, be able to write all the data that is given. Then it will simplify it as and when you want to answer the question. And then we talked about the point of symmetry here. And we were saying what is important here is the time symmetry. Remember, if you know that from A to B is 2 seconds, you will know that from B to C, it must be 4 seconds. So already it has simplified it for you to know that if I'm going to look at the time from A to C, it will be 4 seconds because I know from A to B is 2 seconds. And we are referring to that as time symmetry. And we have velocity symmetry. Remember, let's say I'm throwing the ball with initial velocity, say, of 10 meters per second. What is happening is that the velocity decreases as the ball goes up. As the ball goes up, velocity decreases until it reaches now 0 at the maximum height. So we're saying final velocity or velocity at the maximum height is equal to 0 meters per second. Then it starts again from 0, 1, 2, until when it comes back to the thrower's end at point C there, where we're talking about velocity symmetry, we know that it will be 10 meters per second. The difference is the direction. To say if we said upward is positive, then when it reaches C, it will be negative 10 because it's going downwards. So please be able to divide it like that and have an understanding to say if it's 10 meters per second at C, obviously at G, before it just reached the ground, the velocity will have increased. It will be more than 10 meters per second. So even as you're doing your calculations, you are able to see that I'm expecting my answer to be more than 10 because I've passed point C there. Now we are saying again, the most important thing, remember the constant G is always 9,8 meters per second squared and is always downward. Please don't forget that we always have 9,8 meters per second squared for acceleration is G, which is 9,8 meters per second squared and is always downward. It doesn't matter whether the object is going up, G will always be pulling that object downwards. That's why we're saying it stops for a moment at the maximum height because G is pulling it downward. So don't forget G is always 9,8 meters per second squared downwards. So sometimes we'll say write down the magnitude and direction. Remember, it remains constant. It doesn't matter where, in which part of this vertical motion are we looking for G. G will remain the same, which is 9,8 meters per second squared. I've emphasized the issue of formula substitution. You write your answer with correct SI unit and direction when you are dealing with a vector. So always check whether the question wants you to determine the magnitude of a vector or a scalar. If it's a vector, it's important that you write the answer, the SI unit, and the direction. I've already indicated in terms of the data sheet. Let's look at questions now. On this one, I wanted us to look at multiple choice type of question, as we indicated that there are 20 marks that will come from this type of question. So we are saying a stone is thrown vertically upwards. So you pause there. It's okay. A stone is going upward. We've already said that it will go up, it will reach maximum height. And then return to the thrower's hand. So you are expecting, as we're drawing, you will have you can picture the drawing that I've done before. I've drawn something like that and say this was A going to B, going to C, passing, and it's at the ground there is G. So already you can see that the object is thrown from A, it comes back to the thrower's hand. So it doesn't pass. So we don't have this part. So already you are able to see that C will be a correct representation of our answer, because as you look at that one, it goes up, but it passes the thrower's hand. So you are able to see that we'll choose C there as our answer. Now, as we move to 2.2, we're saying a stone is thrown vertically upwards. So the stone is still going up and return to the thrower's hand afterward. So the same scenario, but now the difference is that we're saying which one is a velocity time graph. So you must be able to see the difference there. And then if you look at A, it goes like that, then it goes back. It's like bouncing or something. And then if you look at this one, it was in one. If it was going up, it only went up, it never came down. If it was going down, it's only going down, doesn't change direction. But when you look at B, you have positive velocity and negative velocity. That shows that it changed the direction. So the object is thrown. Thrown means it has initial velocity. Remember, it cannot start from origin because it's thrown. If it's thrown, it must have an initial velocity, meaning that it's either it will start there on the negative or positive, depending on how you chose your positive direction. In this case, it was thrown upward. So upward was positive. Then it was thrown upward. It reached maximum height. Remember, the maximum height is here where velocity is 0. Remember, we said at the maximum height, the object for a moment will stop. Then you know that after that, it changes direction. It starts to increase its velocity again. So you can see that B is the correct representation of that object that we're talking about. Now, if we look at 2.3, it's saying a ball is released. It's very much important to look at that word released. A ball is released from rest. It's even worse, it's released from rest. But if it's released, you know that the initial velocity is 0. It was not thrown. It was not given initial velocity. It was released from rest. So you are expecting that from rest, from a certain height above the floor, and it bounces off the floor. So this one is not just going to be changing direction. It's going to bounce. It's released. It goes down. It bounces. Then obviously after bouncing, it will change direction and move in the other direction. They are saying ignore the effects of air resistance. Which one of the following velocity time graph best represents the motion of the ball? So you are able to check that, okay, this one, I've already indicated that this will be a nice way to indicate a position versus time graph, kind of a graph. And then if we look at D as well, so I'm saying A is out, the distractor, you can take it out, and that distractor will be your D, because we indicated that it's the acceleration versus time graph that moves like that, where we are even, because immediately when it's straight like that, we're saying it's remaining constant, and our constant we said in this motion is G, that is 9.8 meters per second. So you can see that our G is busy changing directions there, and that must be acceleration versus time graph, not velocity time graph. So you know that A and D distractors, they are not answers, and then you had option of C and D. But for velocity time graph, I've already indicated that we have these straight lines, and you can see that the object, when it bounces, it changes the direction. So this must be the correct graph. So always know how the graph for a bouncing ball, the graph for the ball that is just thrown and comes back to the thrower's hand. Know both the position versus time graph, the velocity versus time graph, and the acceleration versus time graph. I hope that helps you and makes you to be even more confident of this section. Now, let's look now at a structured question. You are given a graph there. It's saying a ball is thrown. Immediately when you say a ball is thrown, you know I talk about a projectile, because we said a projectile is an object that has been given initial velocity. And we said this, it has been given initial velocity, and this statement to say air friction must be ignored is telling you that the only force that is acting on this object is the force of gravity. So you know that we're dealing with a projectile here. Now, from the top of a building and bounces, so you can see that if you look here, you have to look there, it's thrown. So initial velocity was 10 meters per second. And it bounces. You can see that it bounces. Immediately I told you that when it bounces, then it is more likely to change direction. But after hitting the floor, after the bounce, it spent some time there not moving. You can see there between 2 and 2.2. So you can see that it has spent about 0.2 seconds on the ground. Then it changed the direction. Remember, I mean, that was it spent 2.2, from 2 to 2.2. It was at the maximum height. So you are able to see that okay, it bounced. Then velocity was 0. Velocity is 0 there. It's spending some time there. Then it changes the direction. It moves again, and then you can see that it's starting to decrease, and then it becomes 0 again. Then it moves again until 7.71 time there to 8 seconds. So you can see that we have taken 0.2 seconds here. We have taken 8 minus 7.71 as well there as the time that it has spent on the ground until it reaches the maximum height there at the end of the motion as our T. Now let's go to questions. Our first activity was question 3.1. It says write down the speed with which the ball is thrown. So you are able to check and say our initial velocity is 10 meters per second. Then it becomes easier for you to answer that particular question. Now, all parts of the graph have the same gradient. Give a reason for this question. Remember, your gradient is changing y over changing time. So you will see that this will be changing y is changing velocity over changing time. And by definition, acceleration is the rate of change in velocity. So you can see that what is remaining the same there is the gradient, which is acceleration. And we said our acceleration is g, or gravitational acceleration, that remains the same, which is 9.8 meters per second squared. So you are able to answer that question by saying the gradient of the velocity time graph is equal to the acceleration of the object, and the acceleration is constant and equal to the acceleration due to gravity as indicated. So you are able to get that one correct with no problem. Now let's move again to 3.3. The question is saying calculate the height from which the ball is thrown. So this thrower was on top of a building. So we're saying we want to know the height, how high the thrower was. So you are able now, as I've indicated, to say you can't try and deal with the whole entire motion. Deal with the piece that can help you in order for you to be able to answer the question, because you'll have seen that you had initial velocity there, you had your object moving, but you had your object there at 2 seconds. The object had a velocity of 0. So you're able to move from between that motion and be able to answer the question with no problem. Don't forget, we said data collection is important. So write down the given information. Already you know your initial velocity, and then you know that we have the data sheet or our formulas, and then you know as well that we can choose the correct formula that we can utilize to answer that question. We wanted the height, you know the initial velocity, you know the time was 2, you know that acceleration is 9.8, it's a constant, you know the time there was 2, so you're able to do that. There are different options that you can use to answer this particular question, but I think this one is straightforward because you don't have to utilize any other information except the information that you are given on the graph. So you are able to calculate the height from which the ball is thrown. Now this one is saying calculate the time t on the graph. As well, you have information. You know the velocity initially here is minus 25. You know that the velocity here on the line is always 0. So you are able to know that, okay, I have my 25 meters per second here. I have my velocity here as 0 meters per second. So already you have two information that you are having. You can fill it on your table. Your acceleration you are saying is always 9.8 meters per second squared downwards. So already you have the initial velocity, final velocity, you have the acceleration, and then that helps you as well when you want to answer the question. You are able to choose the correct formula, which in this case will be your VF, because you know VF is 0 there. You have your initial velocity, which is minus 25. You have your A, which is 9.8, and your change in time is what you are looking for. So you just have to utilize that formula. You are able to get this 2.55 seconds. Don't forget, you are adding that to the 8. Already, this object has been in motion for 8 seconds. You are taking from here to here. You are saying it's only 2.55 seconds between this and this. Then at t, it must be 8 plus 2.55, which is 10.55. Don't make a mistake of thinking that the answer will be 2.55. You have to add it on the 8 so that it's able to give you that. I hope this has helped you in terms of being prepared, in terms of dealing with the graphs kind of a question. Now, as we complete this one, it's saying write down the time that the ball is in contact with the ground at the first bounce. So you know that the bouncing those dots, our first bounce is in contact with the ground there, which we said is 0.2 seconds. So you won't forget that it was in the ground. You just subtract 2.2 minus 2. You're able to see that it was on the ground there for 0.2 seconds. Now the time at which the ball reaches its maximum height after the first bounce. So after the first bounce, then you are able as well to see that it reached the maximum height at 2 seconds. Remember, here is your 2 seconds. Now, value of x. X, you are able to now look at the graph. If you look here, you'll see we have 27, we have 25. But now, what is now your clue? You have your clue on the graph to see we are having our 27. The last question was, is the collision of the ball with the ground elastic or inelastic? You can see that because now it's spending some time on the floor and there is change in the velocity. So remember, we're saying elastic, we're saying kinetic energy must be conserved. But as the velocity is busy decreasing, you can see that now it's going to be inelastic because kinetic energy won't be conserved. So that will be how we dealt with that question of vertical projectile motion. And then we move to linear momentum and impulse, which is important. Remember, you have to first remember what is momentum. And this is given in your data sheet to say P equals to mv. So you know it's the product of the mass of an object and its velocity. So you just have to multiply those two. You're saying it is the product of those two. Newton's second law in terms of momentum, remember, we're saying the net force is equals to the rate of change in momentum. The net force is equal to the rate of change in momentum. Impulse, remember, impulse is F net delta T. F net delta T, which is when you define impulse, you are going to say it is the product of the net force acting on the object and the time taken when that force was acting on that object. So you know it is the product. The same as you said with momentum, you said it is the product because you are multiplying M and V. Even for impulse, you are saying it is the product of the net force and the time it took when that net force was acting on that object. So please always remember this formula, these definitions. And we are saying isolated system is when the net external force is equal to 0. Net external force equals to 0. We are saying this is an isolated system. The principle of conservation of linear momentum. You cannot really, if you look at momentum, we have many definitions and it's easy to remember them and get this mark. So we are saying please always remember how to state this or to define. Principle of conservation of linear momentum, we are saying the total linear momentum before collision is equals to total linear momentum after collision. So when you state it, you're going to state it as in the exam guideline to say the total linear momentum of an isolated system is conserved. Let me give you this exam tip to say, as long as you are saying state the principle of conservation, what you will do, you will just say total before what you are saying. You say total linear momentum. So if we say state the principle of conservation of mechanical energy, you'll say total mechanical energy. Just like that in an isolated system. So what we are adding there is in an isolated system. Then you say is concept. So that's how you state the principles is concept. It does not change. What you are changing here is only what you are talking about. If you say principle of conservation of charge, you'll say the total charge of an isolated system is concept. So please don't forget how to state all these principles that will be coming across in your examinations. Now the issue of elastic and inelastic collision. So we are saying for elastic collision, we're saying the total kinetic energy is concept. The total kinetic energy and momentum, both kinetic energy and momentum are concept. That is for elastic collision. However, for inelastic collision, we are saying the total kinetic energy is not conserved. Only the momentum is conserved. So please always remember that the difference between the elastic collision and the inelastic collision. Now, just to link our momentum with other things that we have done, for example, Newton's third law. Remember, we're saying there is body A that is exerting a force on body B. Then the issue of momentum, you will see that it's a collision. One body is exerting a force on another one. So you don't forget that Newton's third law will be in application as far as this question is concerned. And they will be changing momentum, which now refers to the final momentum minus initial momentum. So don't forget that will change in momentum will be final momentum minus initial momentum, which is the same as MVF minus MVI, like that. So let's at all times know that that is our change in momentum. So you must be able to know how to calculate change in momentum. You must be able to calculate the average forces exerted by each, which depends on time. You have seen we've talked about F net delta T, which we said is our impulse there. Newton's second law in terms of momentum, we said F net is equals to the rate of change in momentum. Please remember all these concepts. They will be able to help you as and when you answer your questions. Now, always we're talking about strategy and tips. To say, as you are dealing with momentum and impulse questions, we're saying always first read the scenario carefully. Read the scenario carefully and underline keywords. That goes for Newton's laws, that goes for vertical projectile motion, that goes for momentum that we are busy with. We're always saying read the statement carefully, underline keywords. Remember, in the past, we will always show you the keywords by making them italics or by making them bold and all that, and that will be going away, where yourself you must be able to find the keywords for yourself by reading the statement correctly. Please always read for understanding. We're saying, remember that the velocity, the momentum, the change in momentum, and the average force, they are all vectors. And when you talk about vectors, we're saying there must be always be magnitude and direction. So you will always give us the magnitude and direction because we are dealing with the vectors. So we're saying refer to the data sheet when carrying out your calculations. I've shown you the data sheet for this question, which was the data sheet on forces. So you must be able to know where to go and get the formulas that we are having. And we're saying pay attention to the mark allocation. We've talked about that to say your routine questions, you will have now your 3 marks, which is your formula, your substitution, and your answer with correct unit. Now, elasticity of collisions is important here to be able to check whether the collision is elastic or inelastic. As we indicated, you will calculate the total kinetic energy initially and the total kinetic energy finally to compare the two. Please don't compare them at the beginning. Calculate them separately and then at the end compare them and come to a decision. We are saying if total kinetic energy initially is equals to total kinetic energy finally, we are saying if that is the case, the collision is elastic. And we said elastic means that both kinetic energy and momentum are conserved. But if the total kinetic energy initially is not equal to total kinetic energy final, then we are saying the collision will be inelastic. And we are saying you only equate them like that at the end when you are concluding, but you will do the calculations separately. I hope that helps you. Now let's look at a question which is activity 4. We are saying a bullet of mass 20 grams is fired from a stationary rifle of mass 3 kg. So 20 grams. It's important that you always look at the correct SI unit. Remember, our mass must be in kilograms. So you must be able to convert the 20 grams to kilograms by dividing 20 grams by 1,000. So that's how you will convert that. Then you will get your 0.02. It's important that at the back of your mind, always you are thinking about correct SI units to say if I'm given something, it must be in mass, it must be in kg. Like the one where having 20 grams is fired from a bullet. It's inside the rifle. So you can see that the rifle and the bullet 160. So we are starting with two things, which is the mass m1 plus m2, which have the same initial velocity. So all of them, they have same initial velocity here, vi. That's initial. Now they are separating because now a bullet is being fired now out of that. But what is important is that all of them were stationary. So immediately when you're saying all of them were stationary, you know that they are a stationary rifle. It was stationary, even that one. Then you know that we had 0 there. We have 0 here because there was no initial velocity because they were all stationary. So I assume that the bullet moves horizontally immediately after firing. So it moves horizontal in that direction. And then the rifle recoils backwards. So the rifle is going to move. That is the final velocity now of the rifle. To say the rifle, which was 3 kg, has final velocity of 1.4 meters per second. Now, obviously, you are having the bullet now because you have two things. You have the bullet, that is 20 grams. We said you divide it by 1,000, then you'll get 0.02 kg. That is the mass of the bullet. And then you are having, you have to calculate its final velocity. You know this one. So already you know that for the rifle, at least you have 1.4 meters per second and 3 kg. But don't forget the direction because it's recoiling, meaning that it's moving backward. So if you chose forward as positive, it will mean that the 1.4 now of the rifle is now negative as you do your calculations. So already you can see as the question comes, calculate the speed at which the bullet leaves the rifle. So you are able now to be able to see that, okay, initially we had all of them like that, and then you know that you will have your 0. Then for the rifle, you have the mass 1 for the rifle times velocity 1 final for the rifle plus mass 2 for the bullet and velocity 2 for the bullet. So if your bullet is 1, your bullet is 2, and then the mass of the rifle is 1, you are able to write your formula like that. We always encourage you to first write the principle as is, to say the total momentum before collision is equals to the total momentum after collision, that is in an isolated system. Immediately when you write that, will give you 1 mark. But even if you start by writing the formula like this one, we'll still award you 1 mark. It's just nice when you start there, because at least you are reminding yourself of the principle where this one is coming from. So what is left is only the question of substitutions, where you're substituting the 3 kg. If backward is negative, you will have 3 kg. You are multiplying it by minus 1,4, and then you are able to do your calculation. You're only looking for V2F, because the mass of that will have. I will show you now the solution to that. And then when we go to 4.2, we are saying calculate the magnitude of the average force exerted by the block on the bullet. So now you have a new question altogether. So don't be confused now. When you look at the first question, that's what you must do as and when you get your question, because 4.1 is based on this statement. It's based on this statement. But when we move now to 4.2 and 4.3, you will realize that there is a new statement. So always know that this statement is for which part of the question. So this is the preamble. It says the bullet strikes a stationary 5 kg wooden block fixed to a flat horizontal table. The bullet is brought to the rest after traveling a distance of 0.4 meters into the block. So you can see that all of them, they are stationary at the end. Refer to the diagram below. So you have to calculate the average force, and then you have to say how does the magnitude of the force calculated in this question going to compare with the one that the bullet have on the block. Now if you look for 4.1, as I indicated, that you will first always start by writing the principle, and we are saying that will only mark one of the two, even if you wrote all of them, and then you will do your substitution. And as you do your substitutions, you are able now to calculate your VF2. You will have seen that the 3 kg and the 0.02, they were all stationary initially, hence it's 0. So you have nothing there on the left, and then you are able to calculate your VF. You are able to get 210 meters per second. Hoping that you will do that and you enjoy this type of questions. Now, when you look at 4.2 and 4.3, that I indicated that they are based on that statement that is given. The question was calculate the magnitude of the average force exerted by the block on the bullet. Remember, we're talking here about F net equals to MA. But the problem is that, remember, we're talking about horizontal motion. Don't make a mistake of thinking that our acceleration is 9.8. It's not. We're talking about horizontal motion. It's 9.8 for our vertical projectiles. Now, when on this one, you will have to first use equations of motion. So we integrate these topics. You are able to calculate the acceleration first and be able to use the formula F net equals to MA, and then you are able to determine the force, which is 1,102. And we said, how does the magnitude of this force calculated in question 4.2 compare to the magnitude of the force exerted by the bullet on the block? Write down larger, smaller, or remain the same, and I've indicated the same. Remember Newton's third law to say, as you are dealing with momentum, you will always at the back of your mind thinking of Newton's third law to say, if body A is exerting a force on body B will simultaneously exert a force of equal magnitude but in opposite direction. So it must be equal, the force must be the same. I hope that helps you as and when we move. Now let's look at work, energy, and power. Now our last topic in terms of mechanics in your preparation for your papers, to say in grade 10, these topics are not starting only in grade 12. In grade 10, you have done the gravitational potential energy, which was MGH. You have done the isolated system, which we said it means that no external forces are acting on that system. And then we have done kinetic energy in grade 10, which we said is half mv squared. So you are coming with that knowledge. You have done the law of conservation of energy, where we said energy cannot be created nor be destroyed, but it can only be transferred from one form to another. And we said the sum of kinetic energy. So when you are having EP and Ek, when you add them together, the sum of these two, they give you mechanical energy. So mechanical energy is the sum of Ep and Ek. So when we say principle of conservation of mechanical energy, I think we talked about this when dealing with momentum. So the main thing is that as long as say principle, the concept is here, you're just taking it from here. So you're saying the total mechanical energy in an isolated, it must be in an isolated system for it to be constant. So you're saying the total mechanical energy in an isolated system remains constant. So that you have done, and you have done in grade 10. So you are bringing that information and you're going to utilize it here. Now, what is important for you to remember when you're dealing with work, energy, and power is the definition of work, because we are defining work about what it does. We are saying is the product of the force and displacement in the direction. So it's the product of the force and displacement. This is the force, this is displacement, the product of the two in the directions. Cos theta indicate the direction of the force. So it's very much important. Remember, what we must not forget is that when we have the force and delta x moving in the same direction, you will have your cos will be your theta will be 0, and cos 0 is positive 1, which means positive work is done when the force and delta x are in the same direction. I hope you have done that. You are revising now as you prepare for your paper. But now, when you have the two, the force and delta x moving in opposite direction, we talked about tension in the last question when we deal with Newton's laws, to say when the two are moving in opposite direction, then our angle becomes 180. And if you check in your calculator, cos 180 degrees gives you minus 1. And it shows you that negative work is done when the force and displacement are in different directions. So always you are looking at the direction. Where is the force going? Where is the delta x? Where is the movement? Where is the force? If they're in opposite direction, it's cos 180, which means negative work is done. If they are in the same direction, it's cos 0 degrees, which means positive work is done. So I've explained the positive and the negative work. Remember, we are saying if the force is perpendicular or forms an angle of 90 degrees to the displacement, no work is done, because you will remember that cos 90 degrees will give you 0, and then if you are to put cos 90 there, your work done will be 0 joules. So don't forget that you always look at the direction of the force, the direction of the force, and the direction of movement or your displacement. The principle of conservation of energy, we talked to that, as well as the principle of conservation of mechanical energy. Now, work energy theorem, don't forget, given in the data sheet, please ensure you use the data sheet to remember how to state the work energy theorem. We're saying our work energy theorem, we're saying the work not done on an object is equal to the change in kinetic energy. So you are able to do that. And then we have our conservative force and our non-conservative force. Remember, we are saying that for conservative force, we're saying the work done in moving an object from one point to another point is independent of the path followed. However, for the non-conservative forces, is dependent on the path followed. The work that is conservative and non-conservative. Please remember how to define those, because we have them in previous papers where you have asked to define conservative or non-conservative force. Now we have power, which you are saying is the rate at which work is done. It's important because you'll still come across this power when you're dealing with electricity as well. So it's very much important that you always remember how to deal with questions related to this. Now, I've talked to this to say positive work is done when both the force and delta x are in the same direction. So if they're all moving in the same direction, positive work will be done. But if now is at an angle, the displacement is in that direction and the force is upward, we are saying no work will be done. If they are opposing one another, we're saying the angle is 180, then there will be negative work done. So you must be able to have the understanding, when do we say work is done, when do we say positive work is done, when do we say negative work is done. Now, as we move, you can see there, I think you are happy when you see somebody lifting. You can see that it's lifting up. the weight that is lifting is going in the direction where the force is going, then we will be able to say our work there that is done, there is work done there because the weight that is pulling is going in the direction of the force. Even the same on the other picture, you are able to see that there is positive work done. But now let's look at this one. The gentleman is moving, the delta x is in that direction, but the force that is applying on this weight is in that direction. So the force and delta x, the movement is in 90 degrees. So you are able to see when it's like that, that now we're going to have cos 90 there. So we're going to have 0 work done. So it's very much important to know that in this case, there will be no work done because delta x and the force are perpendicular to one another. Is moving at 90, the force is going up and delta x is going horizontal, then no work is done. Now, always we're emphasizing the use of the data sheet, the use of the exam guideline. So it's important to start every topic that you have your exam guideline, you have your data sheet, because this is what you're going to use to do your calculations. Now, as we deal with the steps or skills to say how do you solve problems that includes work. We're saying be able to draw free body or force diagram. Be able to copy the formula. This is a very simple instruction. Copy the correct formula from the data sheet. And don't forget the angle. I just talked about it to say it always looks at the delta x and f. If they're in the same direction, the angle theta is 0. If they are at 90 degrees, they are perpendicular to each other, we said the angle will be 90 degrees. And then we said if the force is and the force and the displacement are in opposite direction, we said there will be the theta will be 180, so a negative work will be done. And we are saying ensure that you are able to substitute in the formula with correct SI unit. You have seen in the previous question where we were given mass as 20 grams. We had to first divide by 1,000 so that we convert our mass to the correct SI unit, because you don't want now to lose marks because you didn't have right conversions. So we are saying this is your data sheet. It will be able to help you. Remember, we're saying, oh, what define work? Oh, you're able to come in and say, oh, it's the product of the force and what and displacement in the direction of the force. So you are able to utilize it there. You are able as well to deal with your issue of gravitational potential energies, MGH. You are able to deal with the issue of kinetic energy, which is your half mv squared. You are able to define. Remember, if we say define power, you are able to come here. It's able now to show you that, okay, power, we know it, that power is the rate at which work is done. And we said the sum total of kinetic energy and potential energy gives us mechanical energy. And we said when we say state the principle of conservation of mechanical energy, all you will do is to say the total mechanical energy of an isolated system is conserved. Don't forget, if you are having constant velocity, you are able to use that formula of P average equals to F average. We use it when our velocity remains constant. So you have an option of using this power formula or utilizing that one. I hope this data sheet is able to help you as and when you prepare yourselves to be able to answer the questions. Now let's look at an activity here. Our fifth activity, we are moving. The diagram below shows a track ABC. So you can see our track now is A, is B, is C. Our track ABC, and then is saying this from B to C is 8 meters. So an object of mass 10 kg. So we are told that the mass of this object is 10 kg. It's released. It's very much important to underline the language there. Released. It's released from point A, which is 4 meters above the ground. It flies down the track and comes to rest at point C. So the other thing which is important as well is that AB, this one is frictionless, so there is no friction here. But from B to C is a rough horizontal section. So you know that when you're dealing with this, we'll talk about that. Then you're able to talk about the issue of conservative force and non-conservative force, because here we're having friction, we're talking about non-conservative force, and here we have FG, we'll be talking about conservative forces. So you're able to see that the other one is independent of the path followed, the other one depends on the path followed. Now, state the principle of mechanical energy, of conservation of mechanical energy in ways. You see, it's important that we've been doing a lot of discussions there to say how do you state the principle of conservation of mechanical energy. Don't forget, you're putting your total there. Mechanical energy in an isolated system is conserved. Now, is the question 5.1.2 and 5.1.3. You can see the other one is saying is mechanical energy conserved as the object slides from A to C. From A to B, you will say yes, from A to B it was conserved. But now from B to C, we are dealing with non-conservative force, which is our frictional force. So it cannot be conserved because of the presence of that non-conservative force from B to C. So from A to C it cannot be conserved because we are disturbed at B to C where we have a non-conservative force. So you're able to answer that question. And then our question with 6 marks is saying use energy principles only. So remember, ask yourself, what are the energy principles that we have done? I think we talked about the principle of conservation of mechanical energy as one of the energy principle, where we said the total mechanical energy before is equals the total mechanical energy after or final. We talked about the work energy theorem, work net equals to change in kinetic energy, and then we talk about the work done by the non-conservative force, which is the change in P plus the change in EK. So those are the principles that we have in terms of the energy principles that you must use to answer this particular question. Now you were able to answer that one of saying state the principle of conservation. Is mechanical energy conserved or not? We said no. I even gave the reason, but there was no need to give a reason because the question didn't ask you for the reason. And then using the energy principles, so you can see here we're using the work net equals to change in kinetic energy. So we are able now to look, because the first thing we must be able to know the velocity, the final velocity is okay. The object was moving from there to there. Remember, initially they said the object was released. That released is giving you initial velocity. To say initial velocity was 0, it was released from point A. Don't forget that. And then you are given the h there, which is your 4 meters. So you are now able to say, to use your formula to say work net. Now on this one we have Fg delta H cos theta, which is your work done there, and then that is equals to change in kinetic energy, and then you are able to do your substitutions, and then you knew that you had your mass, which was 10. Fg is mg, so it's 10 times 9,8, which stands for Fg. You have your h, which is 4, and cos theta, because they are in the same direction, then you are able to do that. And then half mv squared, and then you know that you have both the mass is half. The mass was 10 kg of the box, and then the final velocity is what we are looking for. Initial velocity Vf1, then we knew that it was 0. Then you are able now to calculate your final velocity just here. So it started from 0. We're looking for the final velocity here. You're able to get it, and then it helps you as well when now you are going to now use this B to C to answer the question, because it says calculate the magnitude of the frictional force. So you have now to say, okay, on this one we have work done by the work net, which is the work done by friction, which is F delta X cos theta. You can see we're now using delta X because we're in a horizontal motion. Then there we're using H. So now you are able to do your substitution, and then friction, you know, is in 180, is opposing the motion, and then it's that. Then you are able to get your frictional force, which is 48,95 Newton. So I hope you will practice many of these types of questions, and then there are many ways that you can use. Here we're using the along the BC, which is that motion. You can still use another energy principle, which is the work done by the non-conservative force. Then still it will arrive you at the same answer of 49 newtons. So practice and do both methods of using work net equals changing kinetic energy or the work done by the non-conservative force, so that you know how to utilize any of the two when you are asked in a question. Now, without any wasting of time, we'll move to Doppler effect, which in this case is our next topic. And then you will remember that under Doppler effect, the first important thing is to know the definition of what is Doppler effect. Is to know what is Doppler effect, which we are saying is the change in frequency. I like to look at the formula there that is saying, okay, we're having V plus or minus VL over V plus or minus VS multiplied by Fs. So that as you define, this definition must be able to help you to say we're saying is the change in frequency of sound. So it's the change in frequency of sound detected by the listener. Change in frequency of sound detected by the listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. So it's important that you see that it always starts here to say it is the change in frequency of sound of the source detected by the listener. This one is detected by the listener. Detected by the listener. Why is it like that? Because the sound and the listener have different velocity relative to the medium of sound propagation. We're saying this depends whether it's on air and the humidity and all that. You'll see, we'll talk about 340, 342, 343 as the sound that remains constant there. It's important that we do that. And we must be able to explain using appropriate illustrations the change in pitch observed when a source moves toward or away. You will know that when the source moves towards, we're saying the frequency of the listener will increase, and when the frequency increases, the pitch will increase. But when it moves away, the frequency decreases and the pitch decreases. Let's not leave the wavelength out of it. To say as the frequency increase, it means the wavelength decrease. So towards the wavelength will decrease. Obviously, the distance between the source of sound and the listener decreases when there is movement, relative motion between them. So as the wavelength decreases, the frequency increases and the pitch increases. But as the wavelength, when the object is moving away from the source is moving away from the listener or vice versa, it means now the wavelength increases. As the wavelength increases, we're saying the frequency will decrease and the pitch will as well decrease. And we must be able to solve the problems using the equation FL equals to V, that equation that I pretend there. Please always start by copying it as is. Then look, if it's towards, you know, at the numerator it will be plus, at the denominator it will be minus. So plus over minus is towards. So you know that at the top there you'll have a plus, at the bottom you have a minus. But when we're moving away, it's minus over plus. Please don't forget that, so that you always remember that. Then you must remember the applications of the Doppler effect. We talk about the Doppler effect, flow meter, and all that. Please always remind yourself of those. And then let's be able to explain the redshift. To say here we're talking about these stars that are moving now away from the universe. So the wavelength is increasing, and then that is when the wavelength is increasing, it means the frequency is decreasing, and then we're talking about the red shift. But the opposite of that is not prescribed for that, will be the blue shift. When the wavelength decreases and then the frequency is increasing, then we're talking about blue shift. But in grade 12 we discussed the red shift, where we are saying the wavelength is increasing and the frequency is decreasing. So the stars, as you can see, use Doppler effect to explain why we conclude the universe is expanding. It's expanding because we are seeing these objects moving away from the universe. So you are able to see that the stars are moving away from the universe, which means the wavelength is increasing, hence the frequency is decreasing. Now, I hope that helped us. And then already you know that we have different medium of sound propagation. You will see that the sound travels faster in solids, for example, than in liquid. Solid are denser than liquid. So if it's in water, you can see how the sound is moving. It's moving at 1,500 meters per second. But in air, it's 340. So the denser the medium, the more we have more sound. So you can see that in steel, we are talking about 5,900 meters per second. So the medium is important. Hence, we always talk about the medium of sound propagation. Don't forget the wave function, because it's telling us the relationship now between the wavelength and the frequency. Remember, they are inversely proportional. I was saying to you, as the wavelength increases, the frequency decreases. So you can take from there, you can say frequency equals to V over lambda. So you can see that as this one decreases, this one increases, and vice versa. As this one increases, that one will decrease. So that is the relationship between wavelength and frequency. So don't forget it. As the distance is becoming small, the frequency is increasing. But as the distance, or as the wavelength increases, the frequency is decreasing. Hence, the pitch will decrease as well. Now, that's what I just explained. That is the prior knowledge that we brought. The formula, you have been utilizing this formula. I think by now you know that the FL stands for the frequency of the listener, the FS is the frequency of the sound, and we have the V there, which is the speed of sound in air, speed of sound source. You see the difference now. We have the other one is the sound, is the source. This one is the one of the listener, if the listener is moving, if the source is moving, and then this one is our speed that we said it depends on the medium that you are. In air, it's 340, but sometimes we'll define it for you to say it is 341, it is 342, it is 343. So don't be amazed when we tell you how much the speed is. You just utilize the one that we give you on the question. Now, without any further ado, I'll move to the Doppler effect. I talked about this already, to say moving towards, it will be approaching, it will be plus over minus, approaching or moving away, it will be minus over plus on the formula there, so that you are able to utilize it. You are able to utilize it well. Now, with no problem, we can now move to an activity. They're saying a police car moves away from an accident scene. So already you know that when it's moving away, it simply means that the frequency must be decreasing because it's moving away. And already we have indicated that towards is plus over minus on our formula. Away is minus over plus. It's very much important that those small things, you always have them in you. And then you are able to see that at a constant speed with each siren on, a paramedic at the accident observed 7% drop. So you will see that 7% drop is 7 over 100 is 0.07, which means if we now have 93% of sound. It looks like a small piece of information, but it's important, because if I say 7% drop, it means we no longer have 100%. We now have 100 minus 7, which is 93%, but we have dropped by 7. So you will see 93%, it will give you 93 over 100, which gives you 0.93. So that is the type of sound that the listener is getting in comparison to what when the car was still standing. The speed of sound in air is 335. So you can see that sometimes we are saying it's 340, sometimes we are saying 335. But if we told you that it's 335, you got to utilize that 335 in order for you to be able to answer the question. Now, state in ways the Doppler effect. Remember, you will always start by saying it is the change in frequency of the sound detected by the listener. It is detected by the listener. Why? Because the listener and the source have different velocities relative to medium of sound propagation. So you are able to do that. Then you are able to collect your marks there. Now, with you have to calculate the speed of the car. Then you know the formula. Then we have the question that says an astronomer on Earth observes the missing frequencies in line from a distant galaxy. The frequencies associated with the specific elements are of lower than expected. The frequencies are lower than expected. And then we are saying with what kind of line spectrum is this astronomer working? We'll talk to that. Is it absorption or emission? So you have to remind yourself of absorption and emission spectra. You have to identify the type of shift seen by the astronomer, and then you have to as well, is the distant galaxy moving towards or away from us? So you're able to respond to all those questions. I've already defined a Doppler effect. please know the definition. And then when it comes to calculation, you will write the formula. And then you know towards the issue of towards and away, I've indicated that away is minus over plus. So know that minus over plus for away and then plus over minus. In terms of our frequency, remember is 7% drop. I've indicated we are now left with 93%, which is 93 over 100 is 0.93, which you multiply by that. Then you are able to do your substitutions, and then with no any problem, you are only able to now you had an equal sign there. You are able now to cancel the Fs. You are only looking for Vs, which is 25.22 meters per second. Hoping that you will be able to utilize that formula and be able to collect the marks that you are supposed to collect. Now, this one was saying an astronomer on Earth observed the missing frequencies in a line from a distant galaxy. The frequency associated with the specific elements are of lower than expected. With what kind of line spectrum is the astronomer working? We're saying this is an absorption spectrum. Now we are able now to say, as we move forward, identify the type of shift. So this type of shift we're saying is red shift. Remember, we do red shift, we don't do blue shift in grade 12. So it's important that our exam guideline talks about the blue shift, and then we are able to move, and then we are able to move, and then we're saying is the distant galaxy moving towards or away from our solar system. Remember, we talked about the issue of towards or away. We said away is redshift. Redshift is mean the stars are moving. Remember, we said the universe is expanding. So you're able to look at that and say this must be our answers. It's like our answers already, we know them. That with us, the stars are moving away. We're dealing with our redshift. Now, the topic second from last, so you can see your paper will have all those topics that you will be dealing with. To say now we are moving to electrostatics. To say the following concepts are very important in terms of electrostatics. Sorry for that. We are saying know Coulomb's law, know what is an electric field, know what is electric field at a point. You cannot wake up in the morning to go and write paper and you don't know these three definitions. Please know them. And then the good part about them, we are saying that if you look there in terms of our electrostatics, we're seeing the electrostatic force, the first equation there on the or that is given there, you're able to see that our electrostatic force is directly proportional to the product of the charges and inversely proportional to the distance, to the square. Don't forget that square, to the square of the distance between them. So you're able to state Coulomb's law utilizing that formula. It helps you. Electric field where you are able as well to define, to state or define what is electric field, as well as to define what is electric field at a point. Remember, electric field, we're saying, is a region in space where a charge will experience a force. A region in space where a charge will experience a force. And electric field is given there on your right there. The second formula on your right, you say E equals F over Q. That is your definition of electric field at a point, which is now a force experienced per unit positive charge, which is your force experienced per unit positive charge. So that is the one that we are referring to say that is electric field at a point. When you say state Coulomb's law, you are coming here. The electrostatic force of attraction or repulsion is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. And then when you are saying that one, you're able as well to define what is electric field at a point, which we are saying is a force experienced per unit positive charge. So you are able to get that as well. So it helps us as well. So this data sheet is very useful. So when you are asked the definition, you are forgetting, go to the data sheet. It might be able to help you to solve the problem. Now, without any wasting time, we move to the activity number 7. You can see we've been doing a lot of activities. We are saying the diagram shows two small identical metal spheres, R and S, each placed on a wooden stand. It's very much important to know that they are on a wooden stand. Is it a mistake that we're putting them on a wooden stand? Think about it. Spheres R and S carry charges positive 8 and negative 4 microcoulombs respectively. So you can see that the other one is positive, the other one is negative, and you know that the negative is the one that will donate, or that will lose electrons, that will transfer. A correct language will be that will transfer the electrons to the positive one, because the electrons that do the movement. Now, explain why the spheres were placed on a wooden stand. I'm leaving it for you to think. Why are we putting them in a wooden stand? Why didn't we put them on the ground? So we are insulating them. We're ensuring that the charges cannot move to the ground. So it's important that you have that in mind, to say these stands are important, because we are saying we don't want our charges to move to the ground. Spheres R and S are brought into contact for a while and then separated by a small distance. This one is one question that makes our learners to be confused and to be able to lose marks. So it's important that immediately when we say we bring the two together, so we are having 8, we're adding it with minus 4, we're dividing by 2. So you will be able to do the math there. You say 8 minus 4 is 4, divided by 2 is 2, which means now these charges, all of them, these two, when you bring them together, when they separate, they will now each carry a positive 2 microcoulomb. Now, the mistake that you must not make, look at this question, is saying draw the electric field pattern due to two spheres R and S. Now, you don't make a mistake of writing the electric field pattern for this one. Because for this one, the question, if we wanted you to draw, we would have asked you before this statement. This statement is saying now they've been brought together, which means now we no longer have 8 and minus 4. We now have 2 microcoulomb and 2 microcoulomb. It's very much important, because the mistake you'll make, you will draw the electric field pattern of the positive and the negative. Then they will be joining one another. They will be attracting each other. But with these two, they are now going to repel one another, as you can see in our solution, as we show you how we go about do that. The first question we answered, we said we don't want the charges to leak to the ground because it's insulated. But now on the net charge, we're saying you add the 2, you divide by 2, you get the 2 microcoulomb. And as you draw the charges, you will draw them in that fashion, and then you'll be able to get your 3 marks. The 3 marks is number 1, correct direction. Remember, from positive, the charges must be going away, and then you'll get 1 mark for that. Shape, correct shape of electric field, 1 mark. These lines, they don't touch, they don't cross one another, another 1 mark. So please be able to draw electric field patterns, but be able to draw for positive and positive and positive and negative. Sorry for that. As we move, you are able to see that this is how you do. But the most important thing is we can ask you to draw the electric field pattern for the positive and negative. But in this case, the question was based after the touching. Immediately after touching, they now carry the same amount of charge with the same. If they are positive, the polarity will be the same as well. So it's important that you always remind yourself of that. Now, we say after R and S have been in contact and separated, remember now we are having 2 and 2. A third sphere, and we're bringing now the third sphere, which is T now. You can see now we have T in the middle of R and S now. We have T with 1 microcoulomb. Now, what the information that you know already is that this is 2 microcoulomb. 2 microcoulomb. Now you are bringing T, which is 1 microcoulomb. So you know all of this, so that you are not confused. You are sure of what you are given, because they've touched and they are separated, and you know their new charge is 2 microcoulombs. But now we're bringing the third one in the middle of them, and we're given the distance. Remember the issue of SI unit. Remember, our charge is in coulombs. So you must be able to convert the microcoulomb to coulombs, which is now 2 times 10 to the power of minus 6. 1 times 10 to the power of minus 6 coulomb, and then 2 times 10 to the power of minus 6 coulomb. So sometimes you will be given in nanometers. So you must be able to know that nanometers is times 10 to the power of minus 9. Please don't forget picometers is times 10 to the power of minus 12. So know all this conversion. Look at our distance there between R and T. They're saying 10 centimeters, but you know that the correct for distance, the correct SI unit must be meter. So you must be able to say, okay, centi, I'm going to divide as well there. I'm going to divide there by my 1,000. So you know that now you get the correct answer. So it's very much important that you know if it was milli, you will divide by 100. So don't forget that convention, because you will lose marks based on your conventions. Now, draw a free body diagram between electrostatic force experienced by T due to sphere R and S. And then question 7.5 was calculate the net electrostatic force experienced by D due to R and S, meaning that you're going to calculate F equals to K, Q1, Q2 over R squared for RT here. You calculate the force. You calculate the force again for K, Q1, Q2 over R squared for ST as well. When you finish, because the question says net, you add the two, then you get the net electrostatic force. Then you are able to do that. And then look at this one, we're talking about define electric field at a point. Remember, we said this one is given in the data sheet equals to F over Q, which we said is the force experienced per unit positive charge. Just to write that, you got your 2 marks. Then the last question was calculate the magnitude of the net electric field at the location T due to R and S. So you're going to calculate there. So it's important, as I show you the solutions, you have drawn, remember this one was a free body diagram, you have made a dot on T to say we have now the force exerted by S on T. So it's a force of repulsion. So you can see that T is going away. The force exerted by R on T as well, the T is running away. So you can see that all of them are away because all our repulsion is a positive and a positive. They determine how the movement will happen. As I indicated, you will calculate the force due to ST and the force due to RT. And immediately when you have done that, you add the two to get the net. But what is important here is that as you're getting your net force, you must always check the signs conventions there to say are they all positive or negative and all that, so that you are able now to get your correct answers. And then you have your 1,35 as your final answer towards S or right S, or you can just write S there. So that is that for 6 marks. For the next option, you have to calculate we say you have to define electric field. We define it already. We said it's the force experienced per unit positive charge. We got that from the data sheet. Calculate the magnitude of the net electric field at the location of T due to R and S. Treat spheres as if they are point charges. So the simplest way, you can just use E equals F over Q. Remember, you have calculated your F net in the previous question. So you just say the F there, you divide it by the T there, which is your 1 times 10 to the power of minus 6, and then you are able to get 1,35 times 10 to the power of 6. Don't forget electric field is in Newton per coulomb, the SI unit, because all the time you must be able to indicate the correct SI unit. You can take that longer method. You can calculate the E due to R, then you take Q over R squared. You get E due to S, which is KQ over R squared. You substitute for both of them. For this one is 0,1. For this one is 0,2. Yes, 0,2. And then you get your E net now, which is now so you see the distance, how the 10 was converted to 0,1. The 20 was converted to 0,2. So it's very much important that you do that. As you divide that by 100, you'll get 0,1 by 100. So check your convention so that you don't make a mistake in terms of your convention. And then you are able now to add the 2, and then you still get your 1,35 times 10 to the power of minus 6. So the same method that we have used when you're doing FNet, you are able to utilize that. It's not all the time that you will be given the forces in a line like that. Sometimes they will be forming a right angle, triangle. But the same, let's say you are having R, T, S, you will do the same. You'll calculate the force there, you'll calculate the force there, and then you'll be able to use the theorem of Pythagoras to add them. If you want E net, you will do the same. You calculate the E there and the E there, and then you'll use the theorem of Pythagoras determine that one. So know all the time that sometimes there will be three of them in a horizontal like this, or they can form a right angle triangle where you would use the theorem of Pythagoras. So please ensure that you know all of that. We move to our very last topic as we conclude, which is electric circuits. So we're saying here the first thing that you must know is the EMF. To say when that circuit is open, we have EMF, which is the maximum energy provided by a battery per unit charge passing through it. I find it easier when you look at V, the potential difference as W over Q, then you know that, okay, the difference there between that EMF and that one V is that this EMF is the maximum energy per unit charge, the maximum energy per unit charge passing through it. So that's how you define your EMF. You can just take it from there. The thing you're bringing there is now, this is the maximum energy per unit charge passing through it. Don't forget the definition of EMF. The internal resistance, remember you've done, there is an experiment. There's an experiment as well for determining the internal resistance. You have your Ohm's law. The potential difference across the conductor is directly proportional to the current in the conductor at constant temperature. Now, this one, for the sake of your exam, it's important that you always remember Ohm's law to say, let's deal with the issue of Ohm's law, where we're saying V is directly proportional to current, provided that the temperature remains constant. Remember, you must be able to deal with both series and parallel circuits, and you must be able to know that you have power, and your power is the rate at which work is done. So it's important as and when you are dealing with your electricity. And the most important part, as I conclude the lesson, is for you now to remember at all times that when you are given series resistors, you can be able to calculate the total resistance, which will be R1 plus R2 plus R3, depending on how many resistors are in series. You just add them. But when they are in parallel, we're saying 1 over R parallel is equals to 1 over R1 plus 1 over R2 plus 1 over R3. I know some of you are used to the method of utilizing the R parallel is product R1 times R2 over R1, product over sum. You can use that for two resistors, but if they are more than two, it becomes a little bit different. So it's better to stick with that the one that is given in your data sheet, the 1 over R parallel, and you're able to do. But if you have only two, but always start by writing the correct formula from the data sheet. So I hope you won't forget that. And then in terms of internal resistance, you are going to be dealing more with questions based on that as you move on with the rest of the syllabus. But for the sake of your paper, you are doing Ohm's law as you have done it in your grade 11. So I hope all this will be able to help yourselves as and when you prepare yourself for the paper that you are going to write. You'll be able to remind yourself of all the questions that we have done, all the things that we discussed under this. That is your data sheet, which is very much important in terms of your preparation. Don't forget, when it comes to the law, you are just making V subject of the formula, and you are saying the V is directly proportional to the current. The EMF, we said is V equals to W over Q. From here, you can be able to know that it is the maximum energy transferred per unit, per coulomb of a charge passing through it. So the main thing is the maximum energy provided per coulomb of a charge passing through it. So you don't have to forget that. For series, I've indicated you'll be using R1 plus R2. For parallel, you'll be utilizing 1 over RP, which is like that. You move like that. The Q equals to I delta T. When you are dealing with power as well, you have to know that you have different equations of powers depending on what you are given. So hence, the most important thing here when you're dealing with these types of questions is for you to have an understanding of what is given and what you are looking for. I hope all that which we have done today will be able to help you to prepare for your paper and you will do as many questions as possible and then be able to be ready for your paper. I would like to wish you all the best and thank you very much.